Hello, welcome back to Einstein Mechanics channel. This is Strength of Material 1, Simple Stress and Strain, and this marks the episode 2. I did episode 1 on simple stress and strain. We solved some problems, and today we are going to continue with some of the topics left. Kindly subscribe to the channel and click on the notification bell. It will help. Thank you for obeying. Today, our subtopics, the topics we'll be treating, comprises of tensile test, factor of safety, Hooke's law, Poisson's ratio. As an engineer, as a student, it is very good you know the application of these topics. Tensile test, remember you have to test your materials to know the quality, the strength, the resistance to wear, corrosion, and other forces. It will help you as a designer. Factor of safety. We have to get some factor of safety when we are preparing our materials. I will give you more insight. Hooke's law. Hooke's law talks about the relationship between strain and stress. I did a video, gave a complete idea on stress and strain. So you can check out for the episode 1, Poisson's ratio. It is very good. This gives us a clear understanding about how the size ratio of materials is also applicable in engineering. Let's keep going. This is the tensile test diagram. Don't be scared. It's quite interesting. Materials are being tested, and this has the results produced, the physical results, the graphical results we obtain from the tensile test we made. Let's assume this bar. I have this bar in tension. I hope you remember tension. The material is being stretched. So this material is under the influence of force P in a tensional mode. So you can see it is trying to elongate the size or the length of the material. Elongation is going to occur, and the stress induced in the system. So we want to test the force, the magnitude of force this material can contain or can hold without failing. Therefore, we are to take a piece of this material and go to our lab and test. We also have metal or material testing laboratories and equipped with testing materials or machines. So these machines will help you know the forces this bar can withstand. This is called a tensile test. We can also conduct a test on compression, but in this video and for these studies, we are focusing on the tensile test. So let's see force P. We have the force P applied to this material, and we want to test if this material will fail. That means if it will break or it will be able to withstand these forces. And after some time, what we saw was that this graph was plotted. This is stress against strain. Remember the symbol for stress and strain. So the graph is a plot of stress against strain. Let's take notice of that. And when the force was being applied on the material, this tensile force, when they were applied on the material, this is what happened. At certain points, so we started from 0, where there was no force applied to this bar. And At some point A, what we saw was that this material reached its limit of proportion. What does that mean? That means at a certain region, let's say A, from O to A, as we try to stretch the material, the stress was proportional to the strain. Don't be worried. We will explain much when we get to Hooke's law that will show the relationship between stress and strain. So at A, we saw that as the material was being stretched, the stress was proportional to the strain, meaning if we apply a 2 kilonewton force to this material, the amount of stress produced was proportional to the strain, meaning an increase in stress caused an increase in strain. A decrease in stress caused a decrease in strain. That's for the region A, from 0 to the A. So we can see here as the proportional limit or limit of proportion. So from A to B, what happens? From A to B. At A to B, what happens is the material is no longer in the proportional limits, meaning from A to B, the stress is not proportional to the strain, but although it is in the elastic limits, therefore we call elastic limits. What does that mean? Can you remember a spring? Let's see if I have a spring like this, a spring which I'm trying to pull apart. A force is here and there's another force here, P. When I try to pull this string apart and I release my hand, the spring is going to come back to its original position. Yes. When I try to expand or to apply a tensile force to a spring at a certain level, when I leave or when I remove the applied force, the spring is going to come back. The same thing happens to this bar. When this tensile force was applied at a certain point, it was still in the elastic limits. What does that mean? Meaning when the forces were released, the material was able to come back to its original length. There was no deformation. So if the length was 2 centimeters, when the material was originally made, let's say 2 centimeters, after a certain period at B, we stopped applying the tensile force and the material came back to its original length. No deformation what happened. That's what we call the yield, or we reach the elastic limit. At B, it is still in the elastic limit. Remember, at B, it is not in the proportional limit, meaning the stress here is not proportional to the strain. The stress is not proportional to the strain. And let's look at here. From B to C, there is something happening from B to C. So beginning at this point, considerable elongation occurs with no noticeable increase in tensile force from B to C. So in the diagram, we can see that from B to C, there is an elongation going to happen. Yes, the force are still being applied. This is a process, remember, from O to A. The tensile force were there, and we saw that when we leave applying or we stop applying the force, the material is going to what? Regain its size. The same thing happened to B. It is going to regain its size. But from A to B, the difference is that the stress here is not proportional to the strain. But from B to C, what we see is that as the forces are being applied, there is going to be an elongation in this bar. So the bar is no longer going to remain at its original size. It was 2 centimeters initially. So now it is going to be somewhere around 4 centimeters when the tensile force are being applied. That's from B what to C. It is going to what? Yield. Remember, it is the same force. If we took a magnitude of 30 kilonewton force in tension, so 30 kilonewton force that was applied initially, still none of the forces was increased, but at this point B to C, the material itself is going to elongate. It is called yielding. That's what we call yielding. No one is applying any other force, but at this point it is going to elongate by itself. That's from B to, so you can see that it is a straight line, meaning it is elongating. The size or the length of the bar is going to elongate. I hope you get it. From C to D, there is a phenomenon that is also going to happen. We're here at a place where the elongation started without an increase in the force is called the yield stress. That's what I call the yielding. The process is called what? Yielding. Let's see, from C to D, what happens from C to D? There is a process or there is an activity going to happen. So from C to D, that's what we call the strain hardening. The strain hardening. After it was elongated, now it is going to also again increase in size. Yes, it is also going to increase in size when these forces are being what? Increased. When the forces P here are increased, it is going to increase in size, and at a certain point D, look at here, D, that's what we call the ultimate stress, meaning we will, at this point, the material will be stressed to the highest point that it can no longer contain any other stress. Our main focus here is to test the material strength, how it can withstand stress. So we are trying to still increase the tensile load. So at certain point D, the material can no longer. So that's why we call the ultimate stress. So this will help us know the maximum force, the maximum load. It's quite interesting. It will help us know that, okay, from a force of 40 kilonewton, this material will fail. So even if I add 4.01 kilonewton, this material is going to fail. It is going to break. So I'll write it down as an engineer or as a designer. I now know the elastic or the strength, the stress limit of this material. That's very good. So this place D is called the ultimate stress. So now I decided to apply another force. I'm becoming stubborn here. I know that still this material can withstand some stress, although the test is telling me that I shouldn't increase the force because this is the ultimate stress it can hold. But I'm trying to increase the force. What is going to happen? Let's see. The material now is going to break. Look at the graph. You can see that it is now decreasing. So the size, that's what we call the nickeling. It is going to reduce. So look at the size. So the material is going to be something like this. The size, the middle is going to decrease. You can see that there's a reduction. So it is trying to break. So by the time we see this material will break apart at this point, E. Because when we read the ultimate stress, we were supposed to stop. We shouldn't have applied any other load. If it was 40, that was the strength of the material, the ultimate strength. but I decided to add a 0.1 kilonewton force to it. Then the material will start to narrow. It will start to decrease in its size, going to break. That's what we call the fracture is going to happen. I hope you know fracture. It's going to break apart. And the process of narrowing, that's where the decrease occur, is called the neck length. That's good. That's quite interesting. So this is all about tensile test. So this was just a piece of the bar I was trying to test in the laboratory to know the entire strength of a beam or a bigger bar. This will help me know that when I'm building a structure, I'm going to only use a force of 40 kilonewton on that material. I know that if I exceed it to 0.1 added, the material cannot support my structure because the test gave me 40 kilonewton load. I hope it was quite interesting. That was for the tensile test. Tensile test. So let's try to move again. So let me give you a clear understanding here. So at A, that's what I call that this A. It is perfectly elastic. Perfect elastic. Or it is in the elastic limit. This A. So at A, you know that stress is proportional to strain. And at B, what is the difference between A and B is that at B, the stress is not proportional to the strain, but it is still in the elastic limit, meaning when we release the load, from the bar, its length is going to regain. We try to stretch it. We applied a 40 kilonewton force. 40 kilonewton. When we release these forces at B, the bar is going to come back. The molecules are not going to separate or break. It is going to come back. That's what we call the elastic limits. The ability of the material to regain its length or size when the forces are removed. And from B to C, what I said is that the material is now going to elongate on itself. No force is being added, or even a little force added, the material is going to elongate. That's what we call yielding. So we see the material is yielding, an increase in length of the material without any excess force added. That's from B to C. It is a straight line. You can see that no increase in the stress, no increase. So it's a straight line. From C to D, what happens is that it is going to what? You see, the stress is now increasing. It is going to elongate, but stress is going to increase, and strain is also going to what? Increase. So at D, that's what we call the ultimate stress. This was all the test was going to tell us. Ultimate stress, meaning the overall strength of the material I'm testing was maybe 40 kilonewton. I shouldn't exceed. If I'm to apply or build a structure, let's say if I'm to build a structure for this material, I should only apply an external force of 40 kilonewton such that it will not fail. Remember, we don't want any failure in our activities as students and engineers. So it won't fail at 40 kilonewton. But I try to add a 0.01 kilonewton force to it at the ultimate strength. And what I saw was that it was decreasing. The material size was decreasing. So I was obtaining something like this in the size. I didn't understand. What I would see is that the size would be decreasing. This is what we call neckline. It is decreasing. The size is decreasing. This is what's happening. The size will be decreasing because it is holding excess force. You see, so the force now will be 40.01 kilonewton. We shouldn't do that as engineers. So it will break. That's what we call the fracture mode. It will break eventually. And this is a good idea about how we conduct a test on our material. Ductility and brittleness. The capacity of being drawn out plastically before breaking is called ductility. That's quite interesting. We want ductile materials. And here, the ductility of material can be measured in two ways: percentage elongation and percentage reduction in area. So we are trying to know the amount of elongation that was produced in a material. We are going to either use the elongation that's related to the length, or we are either going to use the reduction related to the area. So let's see, let's show working. Look at this material. I have this bar. I always try to use a prismatic bar. So this material still in tension, tensile force, and I'm trying to stretch it. I want to know the ductility, how ductile is this material. So I know my initial length L naught, that's L naught. And after some time, you see that anytime a tension is or a tensional force is applied to a material, I told you the length increases. Length increases. So let's assume a length was added later as a result of the force pulling the material apart. So the final length from here to the new length is going to give me length final. You can see from here this. So now we want to know the elongation that was produced in this material. It makes sense. So can we say that the elongation here was the final length, because there was an increase in length, minus, so the elongation was final length minus the initial length. This is the elongation produced. The distance from here to the new length minus the initial length will give us this elongation produced. That's quite interesting. So this is the elongation produced, and we know percentage. So percentage of elongation. Why are we using the length for the elongation? It is going to be the final one minus the initial one. So this basically is representing this, the elongation. It is just the elongation that we are trying to establish over the initial length times 100%. So what it means is, if the original length was 100%, what percentage was it increased? So we solve and get an answer for it. We can rewrite this formula as percentage elongation E is equal to the elongation over the original length times 100. And it is going to give us the percentage at which this material was elongated. Now let's look at the area. There's something different with the area you have to understand. In the length, we use the final length and minus the initial length. But look at the area. We are using the initial area minus the final area. Can you guess why? Let me show you. When this material was in tensile, when this was we were trying to stretch the material, what is going to happen to the area? It's going to decrease, right? Yes, look at, if I have this and I'm trying to stretch it, initially the area was this, let's say 4 meter square. It was having its original area, and now I'm going to stretch it and it is going to gain a new length of this size. The area automatically is going to increase to maybe 3 meter square because we are stretching it. Remember, a tensile force was used. So the area is no longer going to be the same. The area is not going to be the same. So that's why we use the initial. The initial area is going to be greater than the final area. So the elongation, so this is quite interesting. What is trying to say, we can assume compression here because the final area is going to be less than the initial area. So the elongation or the compression that was made is going to be the initial one, which was greater 4. It's just an assumption, the 4 and the 3. 4 minus the final area. Because if you use the final area minus the initial one, you're going to get a negative percentage, which is not accepted. It's not accepted. So it is always the initial area. And I showed you why it is the initial area minus the final one. For the length, we saw that the final length was going to be longer than the initial one. So you're going to get positives by subtracting the initial from the final. But for the area, you're going to get negative if you subtract the initial one from the final. So it is always the final minus the initial over the initial one times 100%. It is also going to give us the percentage reduction, how the material was reduced. We'll get an answer for it. Factor of safety. So factor of safety is normally defined as the ratio. Let's take this into memory. The ratio between the failure stress and the working stress. So as you can see here, factor of safety is equal to failure stress on working stress. So when designing a structure, a safety factor has to be taken into account in order to ensure the working stresses keep within safe limits. It has been pointed out that stress is calculated from, so we know that stress is calculated from force on area. We have to know that force on area. But in actual sense, these factors are not known exactly. There are some approximations made, and it is possible we can encounter errors. We can have errors in our calculations. Therefore, it is good we leave some allowances in everything that we are doing. That's why this factor of safety was introduced. So, in spite of all these approximation and assumptions made, a body of theory has been developed which is in many cases can show to agree with experimental results. So let's consider this bar. I have this bar. I want to get a bar of 40 kilonewton for my project. And I'm going to apply, let's say, a compressive force this time around, compressive force to it, P. So I have to test and know if this bar can contain this 40 kilonewton. What do I have to do? I have to run my test and know the amount of stress that can be induced by knowing the force and the area. But remember, I may have some irregular shapes, some approximations, some inconsistencies in my calculation of what? Stress. So I may not get the exact 40 kilonewton force. Therefore, I have to leave an allowance. I will calculate maybe 40, but in actual sense, the force to fill this material will be 39.9. In this sense, I'm going to lose everything I'm going to build. Very good. Therefore, a factor of safety, which is in normal language, an allowance has to be made, or we have to leave an allowance in this material such that any force that I will apply will not fail. So in order to calculate for that allowance or that safety factor, we have to know the failure stress. The failure stress, let me explain it further, will be the maximum stress to fail the machine or the material, the maximum stress to fail the material. So if this bar is going to contain a 40 kilonewton force, the failure stress can be any moment from 40.1 kilonewton, because at this force, this bar will break. That's the failure stress. And the working stress is the permissible stress. Any force less than this 40 kilonewton will be in the working stress. That is the force or the stress this bar can withstand without a failure. So it's always the failure stress over the non-failure stress. That's the working stress. In other formulas, we can also have, to calculate for our factor of safety, we must also know the ultimate stress. But there's a condition we must also note. We must take note of this condition. Always, the maximum induced stress is very necessary. The maximum induced stress should and always be less than the allowable stress. So let's assume the maximum induced stress, which is the stress I'm going to work with. That's, I'm going to apply this stress to my material. Let's take it as 35 kilonewton. This is what the force my work demands. I'm going to apply a force of 35 kilonewton meter to cause this type of what? Stress. And the allowable stress, that's the maximum this bar can contain. This one should always be less than it. So this should be 36 kilonewton meter per second square. You see that? So if I'm going to work with a 35 kilonewton stress, then I should allow the bar to have a maximum stress of what? 36, such that this will not overcome the material, causing it to fail. Do we understand? So my stress to work with, or the stress that is going to cause or going to be induced in this bar, should not be greater, should always be less than what this bar actually can contain. Are we good? So I have my bar to have a 40 kilonewton meter per second square stress. Naturally, it can contain this. Then my stress to induce in this bar should be less than this 40. I can choose anything from 0 to 39 kilonewton meter square stress. This one, the allowable one, is 40 kilonewton. That's very simple to go by. And we can calculate the allowable stress. We can calculate the allowable stress. That's the stress the bar can contain so allowable stress The word say allowable, it can be allowed. The maximum this bar or the bar can contain. The allowable stress is equal to the proof stress. I will explain it further. We will solve examples over factor of safety. The proof stress over factor of safety, or allowable stress, can also be calculated from ultimate stress, the maximum stress on factor of safety. It is very simple. What factor of safety is just talking about is that our materials, when choosing them, have natural stress they can withstand. They already have their stress they can withstand. So we should also not apply a force which is going to cause stresses maximum than what they can hold. And that idea is what we should introduce what we call factor of what? Safety. So if I'm going to work with a 30 kilonewton meter square stress, I shouldn't choose a material having the exact stress as the one I'm going to induce. I should have a material with higher stress content, or that can withstand a stress higher than what I am going to induce. So I can choose from 31 to any number stress to help me in order not for my material to what? Fail. That's what all this is about. So the failure stress, the stress that's going to break the material over the working stress. Do we get it? So if we are getting a high number, any number greater than zero, meaning the material is going to fail because the failure stress will be greater than the working stress. If the number is less than zero, then it is going to what? Succeed, because this working stress will be greater than the failure stress. So let's take note on that. It's very important. Hooke's law. Hooke's law is also one of the laws in strength of material. It helps us in many ways. So Hooke's law basically talks about the linear relationship between stress and strain, either in compression or in tension. So as we can see, we can state Hooke's law as Hooke's law states that the stress in a material is directly proportional to the strain within within the elastic limits. One thing we should know is that it should always be in the elastic limit. It shouldn't cross. So I have my strain proportional my stress like this. Or let me write it. I have strain proportional to stress. So I can bring an equal sign and introduce a constant, and I'll call it E to stress. And this E is called modulus of elasticity, or the Young's modulo, either the modulus of elasticity or Young modulus. Every material has a different modulo of elasticity. Let's take note. I will bring some of the materials and their modulus of elasticity. So if I have this, but can we remember stress is equal to force on area, right? And we also know that strain is what? Elongation on what? The original length. So we are going to deduce a formula here. We're going to make something the subject from here. So from Hooke's law, can we say that the E, which is modulus of elasticity, is equal to stress or stress over strain? Let's get this, stress over strain. So let's bring inside their parameters, where stress is force over area, strain is elongation over the length. So I'm going to get E is equal to stress P on A. This division, this one means division, elongation on length. I can, from the law of what? Division, I can change this to multiplication and reciprocate this one. I'm getting E to be P on A, force on area, times length on elongation. Therefore, Young modulus can be calculated as the force times the original length over area times elongation. This is a second formula we deduce from Hooke's law. This one, this two. Can we further make other parameters the subject? Let's try to make the elongation the subject here. We can say that elongation is equal to the force times the length over the area and the Young modulus. This is the third formula. So under Hooke's law, we are able to deduce three formulas. E, which is stress and strain, and E, which is the force times the length over the area and the elongation. So from this, we can say that elongation is force in the length over area and the Young modulus. So let me give you some materials and their Young modulus. So we can see that steel, anytime you are given a question with steel, the E is equal to 200 gigapascal. That's a huge value. And aluminium is the E, 70 gigapascal. Wood. These are the materials likely questions can drop about. E will be 11 gigapascal. I hope you enjoyed it and you had everything right. Thank you for watching this episode. There are a lot of problems we are going to solve in the episode 3. So kindly check out for the episode 3. I'm going to solve all the problems. I have about 6 problems to be solved to give you more knowledge, understanding on stress and strain. So kindly check out for the problems episode. Thank you for your time.